Okay. Good. Okay. Good afternoon, everybody. It is my real pleasure to introduce you today, Dr. Yikun Wang. As you probably all know, Yikun has been my student, my first student. Actually, I never dared to have students before. It has been a real pleasure to work with Yikun, and it has been more than anything a real pleasure to see you develop into the amazing young scientist you are today, and I'm sure you will have a great career. She started very well by getting a distinguished Burke postdoctoral fellowship at Caltech, and today she will tell us about work she has started in a different direction, although we are still working together with some of you here, in a different direction with my great colleague Catherine Zurich and others there. So without further ado, I'm so pleased to have you here and listen about atom interferometer test of dark matter.
Thank you so much for the introduction. I'm so pleasure to come back here to give this talk. Today I'm going to talk about atom interferometer test of dark matter, and I will focus on the mass range of sub-GeV dark matter. So sometimes you call it light dark matter, and we are trying to use the effect of decoherence and the phase shift from anti-interferometer, which is like surprisingly sensitive to dark matter in this range. And I'm going to tell you how these effects are defined and why our dark matter can be tested in this with this apparatus, and that they can be so sensitive and powerful probe to the dark matter. So this work is in collaboration with a group from Caltech, a student Yufeng Du, a postdoc Clara McGree, and Catherine Zurich, and also a postdoc from Chris Pardo from GPL. So here is the archive number of the paper that actually just came out this week. Okay. So without further ado, let me just go to the very beginning of this story, dark matter. So I think we are all familiar with this slide. So we have very strong evidence to believe that dark matter exists in the universe to be consistent with this very beautiful paradigm that we have been trying to explain to observe the universe. But beyond knowing them existing in the universe, we cannot know very little quantitatively about dark matter. So we cannot just know these numbers here, like what is how much universe is composed by dark matter, what is the local velocity of the dark matter, also its velocity distribution, and the mass density of the dark matter. However, beyond these couple of numbers, we really want to know more about the properties of dark matter. For example, what is the mass of the dark matter, what are the charges, and how do they interact with the visible sector. So over the past couple of decades, there is a huge effort to search for dark matter via different directions. We have direct detection, indirect detection. We try to produce some at colliders, and we also have a lot of actual physical probes, very powerful. So the method I'm going to talk about today is in category of direct detection. So to know exactly where we are talking about today, let me just show this very standard and familiar landscape of dark matter mass. So over the past couple of decades, most of the direct detectional experiments are focused or like devoted to this mass range. This is a very strong dark matter candidate, the WIMP dark matter, where the mass is somewhere between a couple of GeV to a couple of TeV. But the thing is, over the past couple of decades, we don't see a signal from this mass range, and the parameter space of WIMP kind of slowly closes up. So that makes us to think out of this range and explore more of this axis for dark matter mass. So so there are also other very strong candidates and very well theoretical motivated dark matter candidates. For example, if we go up in the mass axis, we kind of have composite dark matter, for example, nuggets, QUBOs, and we also have a black hole, primordial black hole as a possible candidate. So now if you move to the far left end of this axis, we have some very light candidates. fuzzy dark matter and a wide range of ultralight frontier where the dark matter more or less acts wave-like instead of particle-like, all the way up to MeV. So the range I'm going to focus today and the range that we'll have sensitive to is this intermediate range. We call it light dark matter, or sometimes referred as sub-GeV dark matter. So range is roughly from 1 MeV all the way to GeV, the below the WIMP length mark. And there are a lot of theoretical motivated candidates here. You can think about hidden sectors, asymmetric dark matter. I'm not going to read all like feebly interacting massive particles, but nevertheless, we are trying to see these particles, if there is any dark matter, can show up in a direct detectional experiments in this mass range. However, the challenge is already there once we go below the WIMP landmark. If we're trying, for example, the most traditional way to search for dark matter in the WIMP regime is a nuclear recoil here. However, like once you go beyond the GeV landmark, the nuclear recoil becomes immediately difficult. The first problem you bump into is this so-called kinematic matching or energy threshold problem. So here is a maximum energy deposition you can get from a dark matter scattering in a nuclear recoil experiment, and it's controlled by the reduced mass of dark matter nucleon system. As you can see, once the dark matter drops below the nucleon mass, this energy deposition actually quickly dies down, and that becomes
Pointer?
Yes.
Is there a pointer there, or there used to be behind there? Look.
Here, this one.
Oh, either that or the real pointer is there.
I think this one should.
Okay. Because I think it's better. Sorry that I interrupted, but since I see you.
Useful, yeah.
If not, there is one real pointer there.
Yeah. Oh,
Okay,
this is
good.
work. Thank you so much.
Sorry.
So we're talking about this energy deposition, and once the dark matter mass goes below the nucleon mass threshold, this deposition quickly dies down, and it becomes immediately difficult for nuclear recoil. Typical detectors from nuclear recoil experiment to get this energy deposition. And I'm going to leave the second one for a moment and talk about how do we, what are the typical ways people trying to solve this problem in this sub-GeV mass range. So for example, you can think about electron recoil instead of nuclear recoil. That gives you much smaller, much better kinematic matching. Or you can think about the collective citations. A very popular way is to think about the photon excitation, where the photon energy is much smaller than nuclear recoil. And if you go to real low end of this range, you can also think about absorption instead of scattering. That will give a different kinematic matching condition. So beyond this, I think a very exciting thing is another very exciting opportunities actually come from kind of our experimental allies. There are a lot of development in case of the materials. So people thinking about using semiconductors, superconductors, superfluid helium to do all these experiments where you have all kind of advantage. That's a very current program to calculate material response to dark matter scattering and absorption. Also, we can try to develop better detectors to really catch the kind of low threshold excitations. And lastly, is kind of where I'm going today, is a whole development in the quantum sensor community. So not only the interferometers I'm going to talk about today, there are also a lot of development in the atomic clock, which is another very sensitive way to see dark matter scattering. And also we have some optimum centers and cavities. So there's a lot to explore here in case of dark matter direct detection beyond what I'm going to talk about today, interferometers. But let me hold there and come back to the second point here about the momentum deposition. So I was saying that the energy deposition actually gives us difficulty when we go to low mass compared to WIMP, but actually opportunity is from the momentum deposition. As you can see, this is a cross-section, a typical cross-section for dark matter scattering in nuclear recoil. And we also have reduced the mass. And importantly, for a light mediator, I'm going to define this better in a moment, what is a light mediator. But with a light mediator, actually the cross-section goes grows drastically if you go to lower momentum deposition. And that is a feature for direct detection in this mass range. And I will also show you that our sensitivity actually benefits a lot from this low energy deposition regime in the kinematic regime. So now I think I have a kind of defined where I am in case of my direct detection, and now I'm going to introduce interferometers. So that is the apparatus I'm going to use today. So I'm going to talk about atom interferometers, but just to give you a sense of these two kind of quantum sensors, I put them in parallel. And I think probably more familiar is the light interferometers. That is kind of quantum mechanics 101. And the working principle of the light interferometers is kind of very elegant. You have light waves traveling in two passes, and your detector sees the interference pattern, or what we call fringe, at your detector. And the thing is, if there's anything happens along one of these passes, for example, dark matter, for example, gravitational waves, for example, local fluctuations, you're going to see a change or a deviation of the fringe you observe at the detector. So this is how the sensor how the light interferometers work as a sensor. So the atom, well, you are probably familiar with LIGO, LISA, all these exciting gravitational wave detectors are built based on light interferometers. So in parallel, we have atom interferometers. So actually the working principle is exactly the same. So you have waves traveling in two passes, and you see the interference pattern of these two waves. And the first difference is, instead of light waves, here we are utilizing the matter waves from most of the case atoms here. Or like I'm going to tell you, actually it's just not a single atom, it's a bunch of atoms prepared in a cold atom state, Bose-Einstein state. So that is very beneficial for dark matter detection. I'll come back to this. But nevertheless, you have matter waves interfering, and you see some fringes, and anything happen locally, you can see them from the change of the fringe. For example, there are exciting proposals to use this apparatus to detect gravitational wave in parallel to light interferometers. For example, matches that is supposed to happen at the Fermilab. And also another thing I want to mention is this EDGE experiment that is a very ambitious space mission that has super long baseline. I'm going to talk about what is baseline later. And also there are proposals to use atom interferometer to search for dark matter. And actually most known from the literature is to search for dark matter in the ultralight frontier. Remember, that is when dark matter acts more or less waves compared, not particles. So you can, I think I'll talk about this more in next slide, but also you can use as a sensor to find structure constant, as equivalent principle, etc. So there's a whole program to use this apparatus to search for new physics. So now let me move on to talk a bit more detail about how this works and why, in principle, it can be sensitive to dark matter events. So here, I talk about the first difference. It is matter wave instead of light wave. The second difference is how the beam splitter and the mirror works. So different from light interferometers, here the beam splitting and the mirroring are really achieved by atomic transitions induced by the lasers here. So at each step, you just apply the laser, and either absorbing or emitting a photon from these lasers can induce the atomic transition between the ground state and the exciting state. So very naively, you can think about these two passes correspond to a ground state versus the exciting state. And for example, if there is a dark matter passes by when the experiment is running, and if you have a wave-like dark matter that interacts with either electrons or photons, that is going to induce the oscillation of some fundamental quantities in this atomic system. For example, the mass of electron. And this induced oscillation actually indirectly gives you a change of this frequency. That's a frequency, that's a kind of energy difference between these two states. And that will have an imprint on the fringe you eventually observe. More precisely, this can kind of interaction gives you an imprint on the phase change of the pattern that I'm going to tell more about how to define the phase change. So the phase change from atom interferometer can only be observed with a differential measurement. So that means you need to compare two measurements to see the change of the phase. That is why the community has been proposing long baseline atom interferometers, basically meaning you have two atom interferometers sitting on each side of a very long baseline L here. And by comparing the fringe of these two atom interferometers, one has dark matter induction, the other one doesn't, you can identify the change of the phase that's induced by dark matter event. And the sensitivity here largely relies on the baseline length. And that is why most of our experiments are really pushing to reach longer and longer baseline to have a better sensitivity. So as an example, I want to show you this ridge plot I got from the H experiment science paper. This is, as you can see here, this is a sensitivity to the dark matter's coupling to electron and also photon as a function of dark matter mass. And the most sensitive region is somewhere between 10 to the minus 18 to 10 to the minus 10 eV. So that's the ultralight frontier. So this is one way that we can see dark matter in the atom interferometer. But this is not what I focus on today. So in today's work, I'm going to focus on a different effect from dark matter that you can see from atom interferometer. That is an effect from a dark matter scattering with respect to one of these two arms or one of these two passes, or I will refer this as one of these two atom clouds in the nets. So suppose that there's, during the experiment time, you have a dark matter comes out of scattering with respect to only one of these two clouds. And that will cause a decoherence between these two clouds. So without dark matter, your two clouds or two passes are still coherent. That's why you see a very obvious pattern, obvious interference pattern by the end. But if the dark matter only talks to one, you will lose the coherence, and then you will see the fringe starts to become smaller and smaller. So that's what I call a decoherent effect. And of course, you will also induce as a consequence a phase shift. So basically, you can look at the two effects simultaneously, and both will have sensitivity to this dark matter scattering process. As you can see here, I put out a very important quantity for us, that is a spatial separation between the two clouds, because the goal is I only want my dark matter to scatter with respect to one of the clouds. If it scatters with both clouds coherently, you wouldn't get a coherent, decoherent effect. So that becomes, that's why this.
Even the clouds you are referring to are the two sides of that?
Yeah, so it's basically these two, two packets here, two wave packets. So it's kind of misleading to say two clouds because they will be spatially separated, but they also interfere each other. So you can think about this as the two passes these waves will travel, because we're talking about atom interferometer, so it's better to say there are two waves, they travel different passes in space. By the way, this is a space-time diagram. So y-axis is space separation, x-axis is time. So these two local wave packets will travel at a different spatial position. So your dark matter event matter only probes one location instead of the other one. So it's like a localized scattering.
And you were before telling us about the ground state and the excited, and I thought it was
So
each of those. So they are So also the clouds are comparing excited and ground state, or
so I always think about this purple and the blue just as the ground and excited state of the atom clouds. And hopefully this will be more clear once I start to introduce a mathematical representation of this. That will be on next slide. But here, this is a very naive picture of why we have why this delta x is important and why our dark matter event can cause decoherence and also phase shift. So I guess this diagram will be more makes more sense once I well defined. But basically, this is what you'll see in the change of the fringe. So this is the fringe what you expect, and this is kind of the phase of your observed in your atom in your detector, and either the coherence of phase is going to give you a change of the fringe you observe. And I will come back to this diagram in a moment. So I want to, before I go to really details of
That would be like a more significant effect if your dark matter interacts with mirror.
With
With the mirror.
With a mirror. So actually, that is something I think I passed by. So for example, if you use light interferometers to test dark matter, the effect people are looking at is the interaction between the dark matter and the mirror. So here, but the thing is here, the mirror, both the mirror and also beam splitters, right? Like people look at dark matter interacting beam splitter and mirror. So here the mirror is photons. So I think in principle, both mirror and beam splitter are photons. So I think that will be an interesting thing to look at. But here you need to rely on the dark matter interaction between the the dark matter interaction between dark matter and the photons. So we can talk about the kinematic mixing, dark photons. But here the effect we're pursuing is a more brutal false one. We're looking at nuclear recoils. That's why this is the advantage of atom interferometer compared to light interferometer, because we have atoms and you can simply look at dark matter interaction with the nucleons. Actually, it turns out the nuclear recoil is the most sensitive process we can look at if we think about the interaction between atoms and the dark matter. But I think that is an interesting direction to look at, just to look at the photons in this beam splitter and the mirrors. So yes, and before I go to the details of the calculation, I want to mention a couple of signatures of this this method of detection. So firstly, we only require one atom interferometer here, so we don't really need a long baseline. Although the long baseline is probably going to help with the sensitivity of the phase, but here the decoherence, basically the reduction of the clearance of your fringe, can already be observed with one single atom interferometer. And also the phase, you want to measure phase, it takes a differential measurement, but you can either do a spatial differential measurement or time differential measurement. You just do the measurement at 2 different times and you can get a phase difference. And also this delta x, the characteristic scale of this experiment actually roughly tells us what is the mass range that will be sensitive to. So if I just think of the wavelengths associated with this scattering process is kind of 1 over q. Q is the momentum transfer. You can already tell that my wavelength is better to be smaller than delta x. Otherwise, it will both clouds. So with that single condition, we can already do a back of the envelope calculation to see that our dark matter mass better to be in this range here is EV from GeV. But this is already a very wide range compared to most of the direct detection experiments can access to. And I will show you this show better rich plots of this mass range later. And also here, because this is a quantum sensor, yes.
Thank you. So why can we assume that dark matter only scatters with one path?
So if it scatters with 2 paths, you will still induce some imprint, but it doesn't really induce the decoherence. So it's like kind of coherent scattering with both clouds, right? You basically induce the same amount of change on each cloud, so you kind of remain the coherence information between the 2 clouds. I'm going to show how we calculate this, and so the mathematical expression actually confirms this intuition that the decoherence effect is really surprised when you go to our low momentum.
Is there a reduction of probability if you can only detect such event that dark matter only scatters with one path?
So I'm going to calculate the decoherence and the phase shift from a dark matter scattering, and we set the sensitivity, how much you can see the phase shift, how much you can see from the decoherence effect, and these 2 things together will give us the sensitivity, the range to the cross section of your dark matter scattering. Right, so coming back to here, so another advantage we observed here is that this is a quantum sensor. It doesn't directly see the nuclear recoil energy. That is why this is a ultra low threshold energy threshold experiment, so we don't really need to worry about how much energy deposition I can get from this process. And I talk about this a little bit, so actually the low momentum deposition associated with the low dark matter mass actually helps to boost up our sensitivity or the rate. And you can also see this later on. And Second, the last thing I want to mention here is something I didn't mention, but it actually is a very important factor here for good sensitivity, is in the sense that the atoms here. So in the practical experiment, these atoms are highly coherent atom clouds, so it packs like 10 to the 10, 10 to the 20 number of atoms within this cloud, and they're packed in a Bose-Einstein condensate. That means all these atoms are coherent. So that means our scattering process is actually a coherent scattering process, similar to a neutrino coherent scattering, and where we actually get n square enhancement on the rates instead of a typical n that you get from a normal scattering. So this n square actually helps us to have a really good sensitivity. And lastly, there is this signal, because it depends on where your delta x is. So this is the directional signal, and you will get the modulation from the spinning of the Earth if it is a terrestrial experiment. Or like if it's a space mission, you also have kind of orbit modulation. And this is actually helpful in the sense, firstly, we can already get some differential measurement for the phase. And secondly, it also helps us to isolate the signal from the background. So we're not really exploring this feature, but this can be a potential improvement to the sensitivity that we're kind of being pessimistic about. Okay. So this is a summary. Is there any question before I go to the details of the calculation? Conceptual questions.
How large is capital N?
Well, we're talking about 10 to the 10, 10 to the 20 is a huge number. That's why we're really started to get an n square enhancement. And for example, the age, this experiment I show you, we can't get the exact number from the experiment, but there's rumors that they are preparing super large atom clouds. So we still have some upside of this number n for future experiments compared to what we have been using.
The edge is in space.
It's in space. It's very ambitious. The baseline is super long, and it's like interstellar concept. Okay, so now let me really move on to the details here. So firstly, before I start talking about our calculation, I want to put a disclaimer here. So the idea of using decoherence to detect dark matter is actually first proposed by it's blocked. I want to show their paper. I can just minimize. Okay. No. I got it. Here, these two papers. So this idea was actually proposed by Riedel and Yavin a long time ago. Our work is kind of just to reformulate what they did and really fully shows the huge potential of using this method to do detection. We also made some modification on how they did the statistics. We calculate the phase shift more carefully because they are kind of focused on the decoherence, and we kind of translate their formalism to a standard direct detection formalism. Then it can be applied to a lot of more processes that we actually tried a couple of different processes, but the nuclear recoil becomes the strongest one, and we can also use this formalism we reinvented to calculate more processes from, for example, dark matter nuggets, like collective excitation. That will be future work. But anyways, after the disclaimer, I want to continue showing how the math works here. So the system of this atom interferometer can easily be described by two-state quantum systems. So the initial state here is prepared as a superposition, coherent superposition of the purple and the blue states. You can think about them as ground and excitation state. And if there's nothing happen along the way, you will see a coherent pattern by the end. Now, if there is a dark matter event happens, and that will apply this rho matrix to this two-state system, and the matrix can be written down in a most generic open system dynamics. And the off-diagonal element gamma here contains the decoherent and the phase information that you can decompose it to be a real part and an imaginary part. And I will show you why we identify this real part as a decoherence factor and the phi as a phase factor here. I will show you in a moment, just hold on. So basically, after this rho matrix, your final state becomes the phi tilde, and now you can just calculate the change of your detected fringe, just pin together this final state and initial state, and it comes out after simple algebra. It comes to the expression depends on e to the minus s and the cosine phi. So this is how much change you get from your final fringe, and if you plot it, it becomes this diagram I already showed earlier. So the black solid line here is your initial fringe. And if you have a decoherence that happens, so non-zero s, let me put it simple, let me send the phi to be 0 and only look at the effect from the s. What you see is actually a reduction of the amplitude of your fringe. So the reduction of the amplitude, we typically we formally define it as a visibility of your fringe, that is e to the minus s. For example, if you go to one limit, so my s is 0, I don't have any coherent decoherence happening along the way, then what you see is this visibility is 1. So that means your amplitude doesn't reduce. You are going to see the original amplitude. So now if I go to the other limit, if I have enormous decoherence, my s is infinity. So that means my visibility becomes 0. So the amplitude of your fringe reduced to be 0, so you don't see any fringe. So that means you have equal probability to see either the blue or the purple at your final state, so you don't have any interference pattern there. So this is the effect of S, and this is why we call it decoherence. Now another effect you can get is this phase shift. So that is given by this orange lines here. So let me kill this S just for simplicity. So you still have the same amplitude, but then what you see is actually this fringe will move. So that is what we call a phase shift. So here I think we're more or less looking at a 90-degree phase shift. And both of these effects are observable from interferometer experiments. So you can get the sensitivity for both. And actually these two things happen together. So not only you induce S, but you also induce a phi. So we get separate sensitivity from these two effects. Right. So just a very interesting fact, the black line is just like a regular fringe. Actually, all these dots, the blue and yellow dots, are our collaborator he got from experiment set. So these are raw data from the experiment. So it's really cool. Okay, so now we set up, we properly define the coherence and the phase, the decoherence. That's our two observables. The next task is, of course, to calculate the S and the phi from our dark matter process. So the decoherence factor gamma, that's both the S and the phi, can be to calculate this. You can map this system to like a system has been well studied called collisional decoherence, and that is simply the exponential of your dark matter event rate integrated over time multiplied by the size of your target. And the rate here, the really beautiful part of this formalism is the rate can be written down with this standard direct detectional rate for dark matter event. You can find in any review or textbook. The rate is a rate per target mass. So let me just go through quickly about this formalism. This is going to be our master formula. So you average over the target mass, and you have a number density from your dark matter. So rho is the dark matter mass density, and chi is the mass of the dark matter. And there is a distribution of your dark matter flux. So we integral over the velocity distribution of the dark matter. And then you'll have some reference cross-section to tell you how large the cross-section is from my process. This is just a reference one, but this is important because most of the dark matter directed plots, since the ridge plot are plotted against this reference cross-section. And then you integrate over the energy deposition from your process. And the next thing is a mediator factor here. So here we're really interested in scattering process mediated by this phi here. So this mediator factor that is written in this line here, cannot tell you what is the weight from your mediator. And most of the case, people like to talk about two limits. The heavy mediator limit, where your mediator factor is just 1, or in the light mediator limit, where your mediator factor is m chi V naught. V naught is the average velocity of your dark matter flux and over the momentum deposition. So this is actually a important quantity in the sense that it tells you your rate actually prefers a low momentum deposition instead. So that is how we really get a very good sensitivity for light mediator, where we have a huge boost from going to low momentum deposition. And the last factor here, this is called the dynamical structure factor. That is actually the most important and also process dependent part. So all the things in front can be very generic, and the difficulty part applying this formalism to different processes really arises from this dynamical structure factor that tells you what is a response from your target, response from your target with a given dark matter event. So that is what I'm going to talk about next. So actually the dynamical structure factor, we can use one important fact about the decoherence, that the decoherence effect doesn't depend on what is the final state of your target. So according to Fermi's golden rule, you can write this dynamical structure factor as a sandwich of the final state, initial state, and your target response function ft here. But because our decoherence fact doesn't depend on the explicit final state, so I can actually pull out this decoherence factor, and we can really talk about two parts. One part is the decoherence part, and that means what is the response from my two clouds. And another thing is final state dependent one that tells me what is the response from one single cloud. So let me first talk about the first factor here, which has a very clean analytical expression. So it is simply is 1 minus exponential of IQ. Q is a momentum transfer dot delta x. Both are vectors. That is why our signal is actually directional. So despite its simple form, I want to talk about two limits to help you understand what is the sensitive part, what is the most sensitive part of our range. So firstly, if your momentum transfer is really low, so it means the characteristic wavelength of your process is really kind of long wavelength limit. That means you're going to probe both atom clouds instead of one. So it's not a really localized interaction. And in that case, naively you would expect the effect induce the decoherence and the phase stack to be actually suppressed. And you can see this very clearly from just doing a simple Taylor expansion of this P decoherence here. So the decoherence as corresponds to the real part of your decoherence factor actually is suppressed by 2 powers of your momentum transfer, and the phase is actually only suppressed by 1 power. So that means if I go to really low Q, I'm going to have a very small effect from decoherence and phase shift.
So sorry, the momentum transfer with respect to delta x.
Yes.
So I thought, so low momentum transfer means 1/2 is really large.
Yes.
But then, so I'm trying to probe.
So that is a limit that you probe both clouds. So your dark matter interacts with both. The scattering is really very.
So you will not really be in the situation where you were saying that
yes.
Your preferred option is to interact only with one.
Only with one.
And that's what you're going to show.
Yes.
Yeah.
So that is the other limit that we can go is the very high momentum transfer limit. So that means the associated wavelength is kind of small compared to their delta x. So that means my interaction only happens with respect to one cloud. And in that case, you can also do this simple analytical analysis. So this whole thing becomes highly oscillatory. So that's we can actually take an average of this oscillatory function, and you will see the decoherence is 1. Of course, this one you need to pin it with other other parts of the rate, but this one is actually the maximal decoherence you can get from this factor. And the phase is a little bit misleading. So from here you can see the phase average is 2b0, but this is because here we're dropping the direct the anisotropic information from, for example, the dark matter flux. So once we put the flux there, this whole thing becomes anisotropic, and we actually have a phase shift down 0. So this 0 is misleading. But I want to show you how this decoherence becomes maximal when you go to this high momentum transfer limit. So we can actually do some simple mathematical calculation of these P factors. We want to actually integral over this angle here. And this is how my P decoherence depends on the Q and the delta S. And you can see the behavior here actually agrees with this simple analytical analysis. Okay, so the takeaway information message I want to give you from this slide is this decoherence factor roughly tells us what is the ideal momentum transfer I want to reach. So it is simply set by the characteristic scale delta x here. So it's better that my Q is larger than 1/delta x in order to only probe one cloud instead of two to have a large decoherence and phase shift. And just to give you a sense, so the delta x is really the information from the experiment. So delta x is actually also a quantity, a number that experimentalists are really trying to push. For example, if you have just any atom interferometer, a typical delta x you can get is 10 to the minus 7 meter. So that tells me a simple translation Q is roughly larger than EV. And if you do the translation further into dark matter mass, that is about mega EV dark matter mass. That is kind of the already like 3 orders magnitude below GeV. And if we can do really good experiment, like it's really hard to keep the two clouds or two wavepackets coherent when you're pulling them apart. So this is really the challenging part for experimentalists. But there are already proposals to say that I can actually reach a delta x of 1 meter order. And if suppose delta x is 1 meter, that means my Q can be as low as 0.1 micro EV or like milli EV dark matter mass. That is really already the far left end of my light dark matter region. So this is really promising from this simple analysis. Now let me move on to the next part of this.
Sorry,
Yes.
in a given experiment, you say delta x is fixed by the experiment, but
It is complicated. That's the delicate part. So actually the delta x is a function of time. So what the experiment do is they start the two clouds together, and then they use the lasers to pull them apart. And it's typically a free fall experiment. So it like at the same time of free falling, these two clouds are pulling apart and slowly comes back after the mirroring. So this delta x is really a time changing function, but this delta x we're taking is typically the maximal distance you can get from this like time varying process. This is one exposure time or like one time of experiment. But like we estimated if we reduce, for example, delta x to be half of that distance, the rate doesn't change much. So it's only introduced at most a factor of 2. So we kind of think this is a reasonable estimate. But of course, the basic calculation you can do is to make this a time-dependent function. And we also our general formalism here, actually you can easily do that because you eventually integrate over time. You just put a time dependence here, and you can get the most precise like estimate of this. But yes,
Isn't Q delta x always order 1? No.
not really. Like for this whole mass range, like we were talking about from IEV to GeV, you don't always get the Q delta x order 1. For example, if my dark matter mass is like 1 MeV, you don't really go to such a large momentum deposition because, for example, for the light mediator, actually prefers small momentum transfer. Because your momentum transfer, Q is like you integrate over, and that like so basically you have access to both low momentum transfer and high momentum transfer.
If Q is very small,
Yes.
so the Q delta x can also go to 0. Q
Yeah,
times
that is
delta x.
exactly. That is why we have a suppression in that limit. So here, like
So you're saying you prefer small Q.
yeah, so that is a really like interplay between these two. And I'm going to show you on the next slide. Actually, we also don't really go to very large Q. So our Q is kind of an intermediate range, and
Right. So Q times delta x needs to be observable. Right. So
it's not really observable. It's just like if my Q delta x is really small, it is going to kill my rate. Not the rate, like
the phase shift is
the
not
phase
all-
shift and
It
decoherence.
is small, right? So
The phase shift and the decoherence are both small. My Q delta x really small. So it's really surprised.
right. I'm just looking at your phase shift formula. So I think
This one.
there is a
Yes, it is surprised if Q delta x is really small. So even though you
so the
have
phase shift is significant about for small Q, so that the decoherence is not so big, but the the phase
Yeah,
shift is the dominant
exactly.
effect.
So that is a very interesting thing we found, like in the ridge plot. You're going to see the ridge plot later. Actually, it's a very interesting feature of the phase phi is after some turning point, my ridge is actually flat if you go to really low mass. That is exactly because here the phase is not as much suppressed as the decoherence.
So in the calculation of eta, they don't include the phase shift effect?
So they mentioned a little bit in the first paper. So the first paper from Riedel, but not really the second paper. And for the first paper readout,
So their formalism should also include.
Yeah, it includes the phase. It's just that they didn't really calculate the ridge from the phase. So their ridge plot is only from the decoherence, not from like the ridge plot, the coupling versus
So that's the
mass.
main difference between you and the
And yeah, kind of, but we also did different statistics and we kind of rewrite their formalism. Like their formalism is kind of
but
different.
presumably get to the same result. Right? The formalism is.
Yes, yes. In case of the decoherence, if we use their way of doing statistics, we get the same result. Yes. Okay, so this is the first part of the dynamical structure factor. And now the second part here is really the process-dependent one. And here I want to use the example from nuclear recoil to show you the formalism of this part of the factor. So this can be actually easily calculated with two lines. And what you end up with is a function of the number of nucleons in the atom clouds and also momentum transfer and also the atomic mass here. So it looks kind of complicated, but if you break down of these two form factors here, Fa and F, they actually tell you about the coherent nature of your scattering. For example, the first one is cloud, we call it cloud form factor, goes to 1 if your momentum is really small or like your wavelength is really large. That means instead of scattering with respect to individual nucleon, actually my scattering is happening coherently with respect to the full cloud. So as you can say, if I send this form factor to be 1, what you get is another n from this term here. So I have an overall n here that is typically what you get from scattering. Now, if I have a coherent scattering with respect to the whole cloud, I will get another n here. So the atomic mass times Na is the number of nucleons. And that is where the n squared comes from. Of course, you can see here that requires my wavelength to be kind of large-ish compared to the size of my cloud. Otherwise, if your wavelength is really small, it is going to probe individual nucleons in there. And a similar thing happened to the atom, but it's not a significant enhancement compared to the cloud form factor that basically gives you the number of nucleons within each atom if you actually resolve the atom. So basically, in summary, if I'm in the coherent scattering limit where my Q dot RC is much smaller one, I'm going to have an n square from the second part of this dynamic structure factor. So that gives me another information about the ideal momentum transfer. That is when the momentum transfer Q is roughly smaller, sorry, this should be lowercase r, roughly smaller than 1 over RC. So these two scales, one is the delta x, the difference between, the spatial separation between two clouds. Another character scale is the size of the cloud. Basically, these two character scales tells me what is my optimal momentum transfer. Or say what is a momentum transfer I will get most of the contribution from. And lastly, I want to mention a little bit about the momentum deposition. So here in this rate calculation, actually our rate doesn't suffer from a low energy deposition. So that means we can actually go to very, very low energy deposition. That means this is a really low energy threshold effect. So I think now we have everything we need to calculate the S and the phi, the decoherence and the phase shift from a dark matter event. So here I'm showing a calculation for nuclear recoil, but you can apply this easily to other processes. And Before we really see the range, we also need to talk about statistics and also what is the sensitivity from an experiment. So we're employing the standard SNR criteria to the sensitivity, and throughout our calculation, we put SNR equals 1. That's our sensitivity to the experiment. Now you need to decide the background and the noise level of each of the observable. So for example, for the decoherence S, actually we kind of have some background there. And we're being very agnostic about the source of the background. We just get this number 50%. That is how much decoherence you see in a typical atomic interferometer experiments from all kinds of background. So we kind of get this number from experimental list, and we see, and that is how we like pack all the backgrounds into this single number as background here. And the noise level is kind of 1% of the background. And because we're like thinking about multi-environments over a very long experimental runtime, so we actually have a statistical reduction of noise level is standard square root statistics, and that is what enters into the SNR of the decoherence calculation. So now I want to talk about something really kind of exciting for us to pursue is actually estimate each source of the background. It seems to be like a kind of calculation missing from the literature. For example, we can think about, because most of the experiments are going to be space missions, so you have actually a lot of backgrounds in the space. For example, one thing you can think of is the cosmic rays. And for this paper, we're like arguing that the cosmic rays are typically associated with larger momentum transfer.
Why do they have to be space missions?
It's just what they do. Actually, we have 4 experiments considered to show the sensitivity. One is actually terrestrial experiment, and the other 3 are space experiments. It's just
they don't have to be space.
They don't have to be space.
You can bury them underground.
Yeah, you can definitely do. And also, like, I think a benefit of terrestrial experiment is you can put a shielding around it. It's just so odd that most of the terrestrial experiments are like shielded, but once they put it in space, they kind of just remove the shielding and expose it to space environment. So
this is atom interferometry, right?
Yes.
You're talking about, right?
Yeah.
But I thought there was one formula.
Yeah, that's MAGIS.
That's not in space.
That's not in space. So
unless they launched the formula into space.
Well, H is like kind of space version
I won't
of.
object.
They're planning.
I mean, there is a like.
This is taped. I'm sorry.
It is recorded. That was the Antao.
Thanks a lot.
We just like got numbers from different experiments. Sometimes they're really secretary about their numbers, so we try to get the numbers, like most of the numbers we can get for experiments, and we use those numbers to estimate.
MAGIS are very secretive.
Not really, like they just because the published papers proposals, they don't put all the numbers there, so we kind of need to email them and what is delta x here you think. So that kind of scenario.
Where will we MAGIS located? You know, at formula.
It's underground, by the way.
It's a secret.
It's in the 100 meter. In the 100 meter fall of
the Tevatron they use.
the neutrino.
Oh, the neutrino.
It's some kind of a shaft. Right?
Yeah, in
There
the
is a shaft,
in the
yeah.
shaft of the neutrino underground facility.
I see. Very good.
Yeah, so there are both space and terrestrial missions. So like I think the background issue is going to be more severe for the space ones compared to the terrestrial ones. But still we're like kind of just brainstorming what are the backgrounds, and we're really looking forward to investigate all this background more carefully. For example, the cosmic rays. So the cosmic rays typically associated with like higher momentum transfer compared to what you can get from dark matter scattering. And going to higher momentum transfer, we won't have the coherent scattering enhancement. So we kind of estimate the cosmic rays is not going to be a big issue. And also the problem with space mission is there is a huge candle out there, which is the sun. So that means we're going to get a huge flux of solar photons. Actually, like it's very odd that experimentalists don't really estimate this background. So there's a group from GPL. Actually, they're doing a calculation for UV photons, and their conclusion is that no, UV photons are not going to give you a huge background.
Did you say a large flux of solar photons?
Yes.
Oh.
Yes. So like we
Those are the usual.
yeah, I think that's
Sun
one
does
of the
give
big
us a lot of
Yeah.
photons.
yes.
Tends to be.
Right. So like this paper is not really published, like it's still under construction. So UV photons do not seem to be a problem. But then there is like another paper pointing out the MEV solar photons can have this forward scattering. They're really estimating the nuclear recoils for the terrestrial experiments. But it seems that you can get kind of a large cross section from some MEV solar photons from a forward scattering, so that could be concerning. But we're like suspecting the flux of MEV solar photon is really on the tail of the distribution. So probably the flux itself is not just large enough to cause a large background. But this is something we're actively thinking. And the good thing about our formalism is you can apply it to any of these processes. You just change your flux and you change your cross section. That's it. You can just do the calculation. So that is something we're actively thinking about. But nevertheless, for this paper, we just pack everything together, get a number from experimental list, saying 50% visibility reduction is typically what it gets performing experiments, and that's how we estimate the SNR here. And for the phase, actually the phase doesn't receive a lot of background from either gravitational effect, cosmic effect. So we actually trace the phase to be a zero background estimate. And in that case, the standard deviation will be determined by the experimental sensitivity to the phase. And that is a sensitivity well quoted from our experimental papers. So they typically write it as a minimal acceleration they can measure. They typically think that the phase shift is associated with acceleration of the clouds. So that's how they quote their sensitivity, and that translates into the standard deviation of the phase in this using this formalism. And this leads to my next point. I really don't want to emphasize, and also interesting future direction is how this sensitivity can be improved by having very long baseline if you have 2 atom interferometers instead of 1. By comparing 2 interferometers, especially with very long baseline, we're expecting the sensitivity can be improved a lot by the factor of the baseline length. And we're thinking about applying our formalism to really include 2 atom interferometers and see how the phase sensitivity can be improved in that way. Okay, so but now I think I have everything to really show you the rich gem here. And so firstly, these 2 plots are for light mediators, and we're taking the mediator mass to be a fixed ratio with respect to the dark matter mass. On the left, we have 10 to the minus 7 of the dark matter mass. On the right, we have 10 to the minus 3, so that is kind of upper bound when you claim it's the light mediator. And so this is a typical rich plot. We have reference cross-section, we have mass of the dark matter. And in comparison, we put some other direct detection projections. These are really projections instead of real data. So the comparable ones are really from superfluid helium or photon excitations. I think a nuclear recoil maybe probe a little bit of this corner here, for example, from a color centers, but the most sensitive ones are still this superfluid helium, phonons here. So you can see that it's kind of comparable in the kind of higher mass range, but once we go to low mass of dark matter, it's really we have very strong sensitivity from sorry, I forgot to say that the solid lines are decoherence and the dashed lines are phase. You can see we have very strong sensitivities when we go to lower mass. And so another thing I want to point is this gray region. So this gray region is mostly excluded by fifth force experiment. I'm going to explain more how do we consider on other bonds. Yes.
I assume 5% of.
Yeah, that's the next thing I want to say. So we consider fifth force bonds here, and then another bond that is very important to us is dark matter self-interaction. So if the dark matter, if chi composes all of the dark matter, so 100% composition, then most of the parameter space, I think somewhere here, most of the parameter space will be removed, already probed by dark matter self-interaction. So that is why we need to assume this is dark matter subcomponent, where the dark matter self-interaction can be a lot more relaxed.
And if you change that to be, this is like very small amount, very small fraction. So if you have a more, so what is the upper bound that you use? This value 0.05 is about the best you can get.
No, really. We're not like really estimating what is the best one can get. I think it's totally fine to be 10%, 20%. So we didn't do this estimate this number carefully. We just put the 0.05 kind of use in the literature.
And
But
why you take y chi at the edge of the unitarity bound? Or?
So yeah, that is the next. There's a lot of information here. So that is related to the Yn, the interaction, sorry, coupling between the mediator and the nucleon, because we receive a lot of bonds on the Yn. So we need to fix the Yn to show this, for example, the fifth force bonds here. Sorry, we fix the y chi to
Isn't that
get
it's just this rate is proportional to the product of
yes,
coupling
yes.
to the dark matter and the coupling to the standard model. Coupling to standard model at most is 4 pi.
So you fix it.
And then the other one has to be.
Yeah.
To fix it to maximize the sensitivity.
And then the other one is limited by self-interaction.
Yes. Yeah.
Right.
So I should put that part here, but I have it next. So y bar here, sigma bar here is Yn squared times y chi squared.
So, but in that sense, you can increase omega chi by reducing the coupling to dark matter.
I think this is
Optimal.
you can
Increase
increase
the interchange.
you can increase the percentage.
But
Right,
that's
this
the
bounce
only-
will.
The coupling they already optimized, I think.
Yeah.
We optimize the coupling.
Yeah.
Where's your self-interacting dark matter bound come from?
So I think it's from the cluster mergers and halo shift observations. So this is what we take for the self-interaction bound. And this combined with the bonds, all the bonds on the Yn. So these are the combined bonds on the Yn. If you combine this and this cross-section constraint, basically it will remove most of the part of the parameter space.
I would imagine you have because your mediator is pretty light, you have basically some like a 1 over v to the 4 cross section, and you itself have a larger velocity like separation. Because the Boolean cluster are pretty moving very fast.
So you mean like maybe the light mediator can relax this bond?
Right.
What's the V for bullet cluster?
V is like 2,000 to 3,000 kilometers per second, like units of C.
No, it's a 10 to the minus 2.
Yeah.
Usually it's 10 to the minus 3. The variable velocity is 10 to the minus 3. Wow.
Yeah, also I guess you probably
You
don't
can
need to
do
worry
that.
about too much about that.
Well, if it's one order, then
It's a bit wilder than
for G squared, and then yeah, so you gain 2 order magnitude on G,
order magnitude.
but that's G squared.
Yes, okay, yeah, 2 order, yeah, you're right.
Yeah, we can chat about this later. But like we're really taking kind of pessimistic bound from the self-interaction. Actually, it doesn't really move whole parameter space. There's still like corners, especially if we can increase the sensitivity for the phase. There will be if the sensitivity of phase goes lower, then this part won't be removed by self-interaction. So this can really be relaxed if we're doing like kind of more optimal estimate. But this is what we show. I think it's already powerful, but I think definitely there's room to improve this. And yeah, and I think that's all the information. Like,
Why is your plot stop over there? What prevents you to go lighter?
so that is a consideration. Actually, I think it's related to N effective because we have a cosmological bound on N effective, so we need to make sure the phi decouples before QCD phase transition. And in that case, we have a bound on the velocity of the dark matter, like the average velocity. So we need to make sure the velocity doesn't escape doesn't escape halo, and that puts a bound on the mass of the dark matter. So if we go below this mass, the
So
velocity.
warm dark matter, that kind of thing don't concern.
The warm dark matter is also relaxed by assuming a subcomponent.
Oh.
So if we assume like a full component, we need to consider thermalization bound because we don't want it to be thermalized after KEV.
But
But-
an effective probably can be relaxed by subcomponent as well.
An effective. I think our game for an effective is assume phi couples before QCD phase transition. Then we don't need to worry about the ineffective. Actually, is this still a little bit abound here? So this is a contribution to an effective, like assuming the like decoupling before QCD, and this contribution currently is not in tension with current measurement, but it can be maybe excluded in the future. Yeah, I kind of like talk about these slides already, like, but yes. So warm dark matter limit is relaxed if we assume subcomponent. So it's really important here. But otherwise, we have the ridge plot here, and hopefully I have some time to really explain like the curves, why the curves behave a certain way. Here I'm giving you a list of experiments we consider basically correspond to all the colors for different lines. And the Big Hill, Macro, and the GDM are all going to be space missions. And the Pinot here is a terrestrial experiment. And all these parameters kind of covers a reasonable range of, for example, the delta x, how far the people like experiment can go in delta x, and for example, the size of the cloud. So this is a reasonable parameters for the experiment. Of course, like next we can include long baseline experiment to see if we can have some increased sensitivity of the sigma phi. So Magic's age will be like here for the next step.
So since I don't have a feeling of delta x, you already explained. So, but then you have this original estimation that the mass that you can reach is of the order of 1 over the dark matter velocity times delta x.
Yes.
So this is what you're saying there, that
So we have
when you put this bound, yeah, if you have a given delta, so for a given delta x, you could
so it's kind of
play more with the dark matter velocity and reach. So this 10 to the minus 5, as Liantao was saying, I would not be dependent on which delta x from the experiment or
So yes, like the actual calculation is more complicated than that estimate because you have a distribution of the velocity. So it depends on, for example, depends on if your rate prefers low momentum or high momentum, you actually have a different contribution from different velocity. So that estimate, we're just taking the average velocity, but for certain scenarios, the rate probably prefers very low velocity. But overall, I think that estimate tells you where you have these curves to kind of in the knee of the curves. For example, if you for example, here actually the sensitivity goes up exactly because you're outside of that 1 over delta x optimal region, but you still have a sensitivity. It's not like it goes away, it becomes 0. It's just like it doesn't become better and better as you go to lower mass. But indeed, it's kind of all coupled calculations. The velocity is not taken at a fixed value, it varies, and also the rate contributes to which part of the velocity you prefer. Does that make sense? They probably like clear.
you say, yeah, this knee depends on the
Yeah,
delta
this
x.
knee is basically like this knee here, where you have the best sensitivity is kind of determined by the delta x, also a little bit on our cloud, the RC.
Okay.
Right, so next slide is kind of house cleaning on what kinds of bounds we consider on top of our sensitivity. So I don't think I have time to go through all this, but basically we consider either direct detections, as we showed lines on the ridge plot, and we consider terrestrial bounds, and the most severe bound is actually from the fifth force. I think it's from Casimir force experiment, and that basically excludes a lot of, here this plot is taken taken from this paper here as a function of medium mass because we consider light mediator. So the strongest bond is actually from the phase force, and that is why you see that huge gray region ruled out. And we also consider astrophysical bonds. The standard coding actually show up here as well, but it's not as strong as the phase force. And the dark matter self-interaction is really the game killer here. Not really game killer, but it kills the possibility for chi to be the whole component. And we also have the cosmology bond from N-effective, but if we have very small Yn and 5 decouples before QCD, then the contribution is not enough to be probed by current bonds, but probably future, like upcoming experiments, are able to probe this N-effective contribution from the parameter space. So, yeah, and now I want to kind of come back a little bit to, this is really just related to this 1/delta-x, 1/RC argument, but it is more clear once we have the curves and explain what are the behaviors here and where is the need. For example, if you go to very low mass range, so that means kind of the average Q is small, and you have a suppression from the decoherence, but you have an n-square enhancement. And this equation just kind of is an analytical analysis of the trend on this part of the sensitivity. And if you go to slightly larger mass, actually you will gain a stable decoherence because your momentum becomes larger, and you still have the n-square enhancement, and this roughly describes what's the behavior here. And at a very large mass region, you have a maximal decoherence, but you lose the coherent scattering, and this is rich. And you can do similar analysis for the phase, but before that, I want to show you this really kind of sweet spot where you have the best sensitivity, and where you have the sweet spot can be simply estimated by 1/√delta-x RC.
So Yikun, I know you started late, but maybe we should.
Sure. Yeah, I'm almost there. So you can do similar analysis for the phase, and it's kind of, we just do this analysis, and it all this agrees pretty well with what we actually got from numerical calculation. And the last, I hope this is the last slide, is last thing about a little bit about the heavy mediator, because for the heavy mediator, it prefers the rate, prefers high momentum transfer, and there we don't have the coherence enhancement mostly. That's why the heavy mediator case is kind of not optimal for us. And although there's no bound here, but actually most of the parameter space is already ruled out by astrophysical probes. But we're trying to map some other processes into the heavy mediator and explain why they are not as good as the light mediator nuclear recoil case. For example, when we work out some processes related to hidden photons, we can have the hidden photon as a mediator that kinematically mixed with the standard photon, standard model photon. So the problem with this process is that there is this process depends on the polarizability of your cloud, and the typical atom clouds have very poor polarizability. And another possibility is to have the dark photon scattering, where the dark photon can couple the nucleons through baryon number or lepton number. But because the mediator here is a nucleon, so the range is not really good, because this goes back to the heavy mediator scenario. And there is actually an interesting paper, I'll pass this, appeared 2021, pointing out spin-independent scattering between the nucleon and the axion-like particles, but we did the estimate, and again, it's not a very good probe. It only probes the PQ scale up to 100 GeV. So I guess I'll just skip the next slide, because this is just showing our directional signal, and you can have a very strong daily modulation, depends on the time of the day for both the decoherence and the phase, and this can help us to really separate the signal from the backgrounds, and also we can choose what the orientation of delta x is to have kind of local information of the dark matter flux. And here comes to my conclusion. For the time, I'm going to skip the conclusion. Hopefully, I already make the points very clear. Instead, I want to emphasize some of the perspectives that we are still working towards. For example, like using the formalism we write down, we can easily estimate this effect from other processes. For example, a very interesting one would be dark matter nuggets, where you have a coherent scattering between the nuggets and the nucleons. And right now we are only considering scattering, elastic scattering, but we can also consider inelastic processes. And another thing we're thinking about, what about the collective excitations? Would the collective excitation also induce some decoherence? So there are a whole lot of processes we can keep thinking, and then maybe there are other sensitive, like useful probes to certain processes. And also, like this is really a thing I'm really like passionate about, is thinking about the long baseline experiment, how the long baseline can help us to increase the sensitivity on the phase. And lastly, it's kind of fine calculation, and probably it will be interesting beyond the dark matter community that we can really use this formalism to calculate all the backgrounds, cosmic ray, solar photons, and just change the flux. And hopefully that can be useful for experimental communities as well. And I think that would be all I want to talk about today. And thank you so much for listening to the talk.
So there were a lot of questions in the middle, but no, I don't know who's running the seminar.
You were running.
So questions. So Magis, so sorry.
Yeah, I had a similar question. Magic.
Okay, so you didn't get we should squeeze the information from Ronnie. He wanted to talk to you, and we have this. Unfortunately, she was not able to enter Fermilab, so we have a long story there. But maybe we have the questions on the park tomorrow. But so Magis, so there's the Magis 100, and I don't know which is the delta X, because I see that the curve there, of course, you see that goes a bit with the delta X dependence.
Yes.
I don't know for each of these experiments, besides the delta X, which are the main
So I think it's
the main determination to decide on the plot, on the reach.
so the size of the plot is the important thing, and also how many nucleons we can have in the target. This is like, I think size of the plot, nucleon numbers, and delta X. Like,
And those numbers you get it from the experiments.
yeah,
so to say.
some of them like they put it on paper, some they don't, so we need to email them and really squeeze it out.
Okay, what about Magis? Where is it going to sit there? You have an idea, or?
I think the Magis, like the delta X of Magis, definitely not in the Newton range. It's kind of somewhere around 10 to the minus 3, I think. And the number of, I'm not sure. I think like Magis kind of not really optimal, all these numbers, because Magis really presuming the 100-meter baseline. So for these three quantities, it's kind of like just the regular numbers they do. But I think the baseline is going to be a pair here for Magis.
But you don't have an idea where it will be sitting in that curve. You have to wait till they give you the numbers.
Yes.
Okay. Other questions? Comments? No? Okay. We thank Yikun again.